Good morning, ladies and gentlemen. Good morning, members of the IB. Good morning, my fellow classmates that came here deserving to support us. My name is Fernando Pinheiro, alongside Marco Betancourt and Brian Acosta. We are team number 1, ShellEcoMarathon FIU 2013. This morning, let us guide us through the 8-month journey that culminated with our participation in the ShellEcoMarathon this past April in Houston, Texas, during the days of April 4th and April 7th. So, Brian, if we can play the video. We want to introduce our journey in a different way. We want to show you guys first the end result of our project, to then show you guys how we got there. While you guys see some clips of our participation and our testing and regulation of the car, let me acknowledge some of the people that made this project possible. First and foremost, Dr. Tsukanov for being our project advisor. Second, all the professors here, they're sitting in this room, that facilitated our knowledge throughout the 4 years at FIU, or 5. We're glad that you guys were able to help us, and none of this would have been possible without your help. So as you guys see here, a clip of the car participating in the marathon. Let me also give a brief introduction about the competition. The ShellEcoMarathon is a pure fishing competition. So as you see here, our car doing our first lap. Here's our GoPro footage of one of the laps of the car. ShellEcoMarathon is a pure fishing competition where teams must design a car that runs at an average speed of 15 miles per hour or less throughout a 6-mile course. As I said this, the one participation took place in Houston, Texas. This competition also happens in the Netherlands and then in Singapore. So addressing some of the global learning issues, we all abide by the same rules and regulations. So for example, we had to create a body here in English units for a manufacturer to be able to cut, but we also had to respect the regulations of the competition, which are in metric units with SI. So as you see here, the car completing the first lap. This is our attempt on Saturday, where unfortunately after the third lap, in the middle of the third lap, we had a problem with the battery where one of the cables got disconnected and the car died down. So we got the car fixed up again to run on Sunday, and unfortunately you see the result right here. This is our attempt on Sunday. I don't know if you guys were able to see how the car worked. On the left hand side we had the steering system, and on the right side we had the acceleration here with the horn. So this is what happened on the second day. Unfortunately our driver mishandled, and then this was the end result of the car. So for the sake of time, I'll jump right into my part, which is designing the steering and the wheels and brakes. First, the steering. It was very simple. We designed a steering with a steel braided cable with 4 pulleys that went around the driver. As you can see, this left handle here, basically this cable was directly attached to the hub. So as you pull the cable, the wheels were turned. According to our calculation, we didn't have to turn more than 15.8 degrees in order to clear the turns, which are very wide. So steering was never a problem. And our brakes and wheels, we used recumbent tricycles, which are the closest application to what we designed for the competition. So as far as load and braking, recumbent tricycles work perfectly. So with no further ado, I just want to pass along to Brian Acosta, who will talk about the frame and the body of the car.
Good morning. As Fernando pointed out, my name is Brian Acosta, and my job in this team was to do the frame and the body of the car. To get it started, here we have some pictures of the initial frame drawings. As you can see, the picture on the left, the initial frame was actually a very complex one, and it used up a lot of material. So we felt that it was unnecessary for it to have so much material, so we started designing simpler designs. The picture on the right is a simpler design, and this picture right here, the one you see here, is actually our final frame design. It's only missing 2 diagonals in the back, but I'll go into more detail on further slides. Here you can see some of the frame simulations that we ran. We wanted to make sure that it was safe and everything would function and wouldn't fail. We calculated the displacement of the tubes, and it was actually very low. The highest displacement was only 4 millimeters, and the factor of safety, the lowest factor of safety was 11.4. So it was basically safe. Moving on to the body. Here you can see some of the initial designs that we made for the body. Here are the initial 4. You can say that the first 3 were the first generation drawings. After that, we went on to move to the second generation drawing, which was the fourth picture on the bottom right. And as you can see, yeah, the one thing that all those drawings have in common is that we intended for the wheels to be inside of the body in order to improve the aerodynamics of the car. But as you can see in the next slide, we actually had to make a lot of changes to our drawing, to our design, because of constrictions, because of the frame and the size of the engine and the location of the engine. In this picture, you can see that only the back wheel is being covered by the body of the car. The two front wheels would be on the outside of the body. Our final design, as you can see here, is a front view picture of the body and a side view. Just to give you some specifics, the maximum height of the car was 29 inches, the maximum width was 27 inches, the length was 101 inches, just a little under 9 feet, and the driver compartment where the driver was actually sitting was 54 inches. That means that it had to be a driver that was 5 feet or lower, which in our case is what happened. We had one driver that was 5 feet tall and the other one was 4'11". Now moving on to the engine selection, Marco's gonna explain to you the process.
Okay. My name is Marco Betancourt. I am the engineer responsible of choosing and implementing all the powered systems in the vehicle. We began this assessment by finding out how much energy was required by the vehicle in order to be propelled and how much power would be needed to produce this energy. So based on acceleration parameters and expected drag, we came up to a number that was about 2 horsepower for our engine power. So we continued to choose, make a database of engines, and we found all of them between 20 cc's and 50 cc's. All of them are 4-stroke due to competition guidelines, and the parameter that we used to choose the engine was based on the compression ratio that the engine could achieve. We didn't do any modifications to the engine itself, so having one that was stocked with the highest compression ratio was very important. So we found the GY6 Scooter engine, which is a 50 cc engine, and has the highest compression ratio in its class at 10.1 versus other engines designed for utility applications like lawnmowers, which are 8.1. We also chose that engine because it had a lot of the auxiliary systems that we needed for the vehicle, and it also had a large aftermarket of parts that we could use to modify it and improve it. To continue with the improving of the engine, one of the items that has the most inefficiencies is the transmission. It's a continuously variable transmission, and we address these inefficiencies by choosing parts from the aftermarket to reduce friction in the CVT. Also decrease the engagement speed of the clutch when based on the engine speed, and also increase acceleration at the expense of velocity or final velocity. So once that was set up, we continued to produce the electrical system for the engine. We began this by getting the same electrical wiring harness that came off the scooter where we got the engine from, and we stripped it down through all the necessary auxiliary stuff that the scooter came with, and included just the signaling lights and kill switches that the competition regulations specify. One thing to know about the electrical system is that we used a lithium-ion battery, which failed halfway through the competition. So just as the big plane companies are having problems with them, we did too. So going with a lead-acid battery is the way to go. Then we have to produce the fuel pressurization system because the competition guidelines say we cannot use an electrical fuel pump to pressurize our fuel. So we created the system. It includes a soda bottle that's a pressure vessel. It's rated to 200 psi, so it was never an issue, a safety issue, because the maximum pressure of the system goes only up to 70 psi. The system includes gauges that let us know the pressure both in psi And in bars, they also have a regulator to reduce the pressure from 70 psi down to 36 psi, which is the operating pressure of the injector. We include a safety release valve that pops at 70 psi and a shredder valve that, in order to be able to fill it up, it's the same valve that you find in bicycle tires. Once we have this set up and the electrical fuel injection system was powered on and running, we were able to begin engine tuning. We found that we had to purchase a wideband O2 sensor so we can finally control the air-to-fuel ratio and program it so that it would maintain the stoichiometric combustion, optimal stoichiometric combustion throughout the whole fuel line. So we did some testing. We had to make our own fuel maps for this, and we had one problem, which was that the ECU would not start functioning closed loop system before like 3 minutes after the engine was started. So we had to really fine tune the fuel maps. Then we had to select the tires. The tire selection was important to reduce rolling friction, rolling resistance, and we chose for the front end of the car 2 of the Michelin tires that are designed specifically for the competition, and they have the lowest rolling resistance in their class. So we went with those. For the rear wheel, since we have an engine that's based for scooters and that accepts a wheel directly on its axle, we had to either modify a bicycle wheel to accept this tire or go with a scooter-based tire. So we went with a scooter-based tire, and we got the one that's slick, so it minimizes the rolling resistance. Now I'm gonna pass it on to Brian to talk about manufacturing.
Hello again. Just to start talking about the manufacturing process of our car, I'm gonna start it off with the manufacturing of the frame. Obviously, because this is a super mileage competition, we wanted our car to be as light as possible. Because of that, we chose to build the frame entirely out of carbon fiber. What we did is we used a really innovative method to join the carbon fiber tubes, as obviously carbon fiber cannot be welded together. So what we did is we started by getting some carbon fiber toe, as you can see in the picture of the left, and we wrapped that carbon fiber toe around some mandrels. Once we applied resin to those to the carbon fiber toe, the end result was here, as you can see in the picture of the right. The carbon fiber made basically a solid U-joint piece. In the next picture, you can see the end result of that. What we did afterwards was that we used the carbon fiber toe and we wrapped the loop side of the U-joint in order to reinforce it. Once we applied more resin onto that and that dried off, we went on to the next part where we started attaching those U-joints to the actual carbon fiber tubes. As you can see in this picture, the end result was that we wrapped it around more, and then the tubes, as you can see on the tips, it has the loop. In the next picture, you can actually see the entire frame. Here what we did is we tied everything with zip ties in order to make sure that our calculations, our dimensions, everything was correct, and that we wouldn't have any problems. As you can see, everything would be connected here with the loops, and the connections would be done to the carbon fiber tubes. In the next picture, you can see the actual end result of our frame. Like I said before, we used even more carbon fiber to wrap everything together, and once we applied resin to that, we had a pretty nice solid piece attaching all the tubes together. Here in this picture, you can actually see the entire frame assembled with everything already mounted onto it except the body of the car. Now to start talking about the manufacturing of the body, what we did is we used the hot wire foam cutting technique. What we did is we cut some foam, but the manufacturer requested that we provide the cross sections of the body every 3 inches in order for them to cut the foam into the respective cross sections. In this picture, all the way to the left, you can see the cross sections as they're being put together. In the middle picture, you can actually see how the entire mold was cut to an upper and lower mold. And on the picture on the right, you can actually appreciate the entire geometry of the body. Here you can see that what we did afterwards was we applied a coat of resin onto the mold and then a furring filler in order to fill out the holes. After that, we laid down some fiberglass. We actually laid 4 layers of fiberglass, and then once we did that, we did some vacuum forming for the body of the car. Here is basically our end result for the body. We were mostly pleased with the result of our manufacturing.
I'll just briefly touch on project management in 30 seconds. As far as the project timeline, we obviously delivered the car. We finished the car on April 1st, 3 days before the competition, and we shipped it through a shipping company by air, so we were able to get that on time. On the next slide, you see our cost analysis. The total cost of the project was $10,000. We expected in the beginning to be $7,500. We were able to get $4,000 funded through sponsors, and the ended up total cost out of our own pockets was $1,900 each person. We had a budget of $2,500 each in case we had to pay out of pocket. So even though the project was more expensive, we paid less out of pocket than what we expected. On the next slide is our division of labor. We both worked equally on the car as far as manufacturing, report. We divided all the tasks in design, so we're pleased about that. On the next slide, this is just a picture of a vehicle in a race. Thank you very much, and we're now open for questions.
Questions?
Would you guys be partners in a, did you work closely enough together that you remain friends?
Yes, that's a very interesting question, because throughout this 8-month journey, we really had a lot of arguments and a lot of this and that, but because of the outcome of the project was so successful in our view, because when you go to a competition, you see teams from universities and high schools that have been doing this project every year, and what they do from year to year, they just tweak a little part of their car to just improve some mileage. And you see their teams are composed of from 6 to 8 people, and we built this thing just the 3 of us, with some help from students that are not part of FIU, just one person. So it was really hard. We had to push each other, and there was some times where we got in a little conflict. But today, we literally built this bond that we're like a little small family, but we're very happy.
All right, so you had a taste of group dynamics, huh?
Absolutely.
All right, did I hear that $2,000 was spent from each of you?
Yes.
Yeah.
Wow. Okay, all right.
Inductive, sorry.
Okay, questions I want to ask. You finished the car 3 days before competition.
Yes.
Did you have any chance to do any fuel efficiency?
That was our only problem. We didn't have the time to test the car before we actually shipped it to the competition.
And with it getting damaged, you didn't get any kind of a taste how fuel efficient?
The only taste we could see is that after the 3 laps, we knew more or less how much fuel we had spent, but no exact number.
Any indication of kind of number that would be? Because isn't that kind of like the goal?
Yeah.
Yes, but since we couldn't get a metric out of how much fuel we spent, so we don't have a number for that.
Okay.
But we did tweak the engine so that it would consume the least fuel possible.
Okay, I was impressed with the fact that you passed all of the entry inspections.
Yeah, it's very hard.
That's tough to do, and I commend you for that. Now retrospective, okay, now I'm doing a re-engineering scenario here. Knowing what you know today, and you went back into your design, how would you change your design today?
Can I go?
You start.
Yeah.
Since probably like halfway through the project, we've had this little joke going on between us that our biggest section in the report would be the section called hindsight. There are so many things that we would change about this project. Even though we were very pleased with the frame of our body of the car, which actually I forgot to say weighed less than 15 pounds. I still think that it was the wrong choice to do a frame for the car. I still think that the best way would have been to just make a monocoque out of the body. It would have been so much simpler to do that. Other than that, the method that we did our body, I was happy with the result, but ultimately as an engineer, I think it was not the most efficient method, mostly because we manufactured the foam, and then we had to sand down the foam. Then we applied a layer of resin, then we did some fairing filler, then we did more sanding, then we did a paint cone primer. The bottom line is that we added so much material and we had to do so much sanding that I feel that the precision of what we drew in SolidWorks is not the same, it's not reflected on the body of the car. Generally, the geometry was pretty similar, but if precision was very important, I don't think I would recommend that method to someone else.
And again, really where I was kind of going with it is you had the car hit a curb.
Yes.
When you were designing it, did you anticipate Could you have put some more safety factor into your structure to ensure that that kind of?
That was solely
it-
like a driving, she just got nervous and lost.
I understand, but the odds they hit the curb, take the average driver here, how often do they hit curbs? So, would you think about, retrospectively, again, fortifying the suspension, 'cause I know I read and you were talking about you would change the suspension. And laying down like that, it'd be hard to set up a steering wheel so that you could actually still see.
Well,
It's a hard thing to do.
To address that, the video only showed when she ran into the cones. It doesn't actually show when the impact of the car
She
happened.
hit the curb, right?
After that, no, there was much more after that. The problem is we got scared and we stopped taping, of
Oh.
course. But she actually
She kept
ran
going.
into the fence and
Okay.
she cracked the body of the car and she broke a carbon fiber too. That's
Okay.
why the wheel was dangling. But the point I'm trying to make is that it was actually a pretty solid impact, and her as a driver, nothing happened to her. She might have gotten like maybe one or two bruising from the safety harness, but essentially I think that our car was pretty safe because nothing happened to her.
Okay, thank you.
Is that
That's
right?
fine, that's good.
Okay. Dr. Basil?
So, just going back a little bit to the fuel efficiency, how exactly were you going to measure it? I mean, you couldn't measure it for 3 laps, how are you gonna measure it for the 6 laps or the 10 laps, or how many
The
ever
people
laps?
who run the competition, they actually put a little sensor on your car.
Okay,
But
so you
since-
couldn't get the data from that sensor or anything like that?
No, we didn't.
The sensor is to measure how many laps you've been around.
Okay.
Once that you go through the last lap, they take your fuel tank off and they measure the contents of it. Whatever is left, they compare it against then another full tank,
Sure.
as it was when the race started.
Right.
And based on that difference, they come out with some equations, they come up with the metrics.
So
of
you
how much
guys
fuel
could
we
probably
can
have done that, right? I mean, you knew,
Not
you know.
precisely. Our
you
fuel
did 3
tanks-
laps, right? If you
fuel
know
tank-
how much fuel was in to begin with and how much came out after.
We did like, at the site, we didn't have
Sure.
access to our pipettes on measuring devices or a scale.
Right, so, but you
officials
have a
did.
fuel tank, right? You could close it
Yeah.
up. Anyway, it's fine,
Yeah,
it's
that's
no
fine.
big deal. I'm just saying, for future, when your big thing is, we're measuring miles per gallon, you gotta have a way to measure that, no matter what, I'm just saying.
I mean, just to put it
give
in
you an idea.
perspective, to make it easier for you to
Uh-huh.
visualize.
No, I understand, we don't have to
No,
go
no, just to
on.
put
It's
some
fine.
numbers
Yeah.
out there, the last place, as you can see on, I think section 8 or 9 on the report, the last place car that actually got ranked, that was able to complete the 6 miles in 250 milliliters, which is the size of the fuel tank,
Mhm.
did 47 kilometers per liter. So if we would have completed the 10 laps, which we would have, that would have been probably the lowest number we would have gotten. Anything above than that would have been.
Yeah, I mean, you can say that, but you probably need to measure that, right? So, anyway, I have a quick question about the use of carbon fiber. I think a lot of times, all of you guys, everyone thinks carbon fiber is the lightest thing, right, no matter what. Did you investigate any other materials for your frame so that way you didn't have to go through all of the additional manufacturing problems that you had with that? So for instance, in the SolidWorks drawing that you had, you said the displacements were very small. Did you take a look at, say, aluminum tubes and see what the difference in weight would be?
We did consider aluminum and we also considered magnesium. But the thing is, we heard that magnesium was really hard to weld. Aluminum, we didn't pick aluminum because of the weight. We just.
What about
So
just
what was the
aluminum
difference in
joints?
weight? Yeah.
Just the joints?
Right.
So that you're making fiberglass tubes, which is pretty easy to do, and set up all of those joints using aluminum transition points or something.
Well, again, it goes down to the weight. We did the joints with carbon fiber. Even if it wasn't that much, we know that carbon fiber is lighter than aluminum, even if it is just the joints, but we saved a couple pounds in there.
But you need to specifically state, carbon fiber is technically less dense than aluminum, right? But with the additional manufacturing that you put on it, you need to state that that is lighter. Just because carbon fiber is less dense doesn't necessarily mean that your specific design weighed less, right? So for instance, you can use that same SolidWorks drawing that you had, put aluminum in there, compare the two weights and say, look, we're saving 10 to 15 pounds if we're using carbon fiber. You know, certainly carbon fiber is a, designer material, but every time everyone comes up, it's, oh, we're using carbon fiber because it's lighter. Well, that doesn't necessarily solve the problem. Anyway, I think you guys did a great job, so don't.
Thank you for the feedback.
All right, let's give them a nice round of applause.